My name is Steve Maher. I'm with Risk Management Professionals. What you're participating in today is an extension of our process safety management and risk management program activities. And what we try to do is, as part of our outreach program, is provide various topics of the technical nature associated with getting good quality process safety management and risk management programs done. The format for this is we're using WebEx to broadcast this as a webinar. So I'll be kind of diverting my attention a little bit to the audience that's tuning in and also the audience that's joining us. Thank you, guys. And what we're going to be doing is reviewing the presentation over the next hour or so. A little bit about logistics. For those of you who it's the first time doing this kind of exercise, this does provide two-way communication. That is good and bad. It does provide an ability to interact with the various participants, and we'll have an opportunity at the very end of the session for having kind of a general forum for people to participate or for question and answer. And I'll give you guys a little reminder to start formulating questions. Because it is a two-way communications mechanism, we're going to keep everybody on mute until such time as towards the end. That way, if you have side meetings, cell phone conversations, or just rustling papers as you're getting other things done in your office, it's not going to disturb the other participants. If you do have technical problems, there's the number on your screen, 877-532-0806. We'll get you through to somebody who can help you out. Also, if you're already logged on, you should have a chat window or an ability to open a chat window where you can communicate directly with our producer, Solveig Sather. And what is the producer's name, Solveig?
RMP Corp.
It'll show up as RMP CORP. And that's the communication you want to have if you want to talk to the producer. You can use that to identify technical issues. You can also use that to formulate questions or interject comments if you wish. This is meant to be as interactive as you want. This is really a mechanism for us to share some tips on how we do our analyses that are associated with PSM and RMP. Also, what you should be seeing on your screen is a PowerPoint presentation that displays most of the screen, and probably in the upper right-hand corner, you'll see a small video image of the presenter. That's me. And if you get tired of that, you can shrink that to your heart's content and then just focus on the presentation. And you should also have copies of the presentation materials that were emailed out last night by Solveig Sather. So let's go ahead and get started. Consequence analysis is a very broad topic. It requires a lot of expertise, a lot of computer software models if you're going to do a lot of details. My objective is to provide a framework and an overview of a lot of the key things that you need to be concerned about with offsite consequence analysis, and especially as it pertains to HAZOP facilitation. For those of you who partake in that art, you realize that there's a lot of thinking on your feet, trying to understand the system dynamics, and understanding the overall consequences associated with severe or episodic events can be very, very helpful. So that's really my objective today, is to provide an overview of those things that will help you to understand consequence analysis and use that understanding to help you understand scenarios that you may be discussing during the HAZOP. So the way I want to approach this is to first of all make sure we're all talking about the same kind of thing when we talk about risk. I want to talk to you about what's the regulatory framework for doing these kind of things, and also separate that from what you can get into if you need to get into a lot of detail. I want to give a general overview of the kind of things you need to consider with modeling parameters, then focus on flammables and toxics, and really an understanding of release phenomenology and what can happen to gases or other acutely hazardous materials if they are released. I want to give you a couple of examples of some different chemicals that not only are very common, but kind of illustrate the range of things you need to be concerned about with respect to consequence modeling. So let's go ahead and start with making sure we're all talking about the same thing when we talk about risk. Risk is really the product of probability and consequences. Likelihood or probability by itself doesn't really give you a complete picture. If something is very likely but relatively inconsequential, it's not really going to be all that important to worry about. Something that may be extremely high consequence but very unlikely is something also that maybe is not all that important to worry about. So it's really by understanding both the likelihood of an event, an undesired event, and also the consequences of it, then we can understand risk and the overall importance that those undesired events play in our lives, in our workplace, etc. When you're looking at engineered systems, you're really looking at a lot of different things that can happen for a complex process system, for example, and it's really the summation of all the individual probabilities and consequences for each of the events or undesired events that can occur. And also, one of the key concepts to keep in mind is individual risk versus societal risk. Societal risk takes into account the number of people that may be affected by the event, whereas an individual risk integrates the number of risks that an individual may be exposed to. Both of those concepts play a role in our understanding of risk and in its quantification. So let's look at some different representations of risk. One of the most common ones that you've probably been exposed to is a risk matrix that might be used during a HAZOP study. On the left, you'll see frequency with increased frequency going up. On the bottom, you'll see severity with increased severity going to the right. And people usually qualitatively assess these, or I've also put some numbers on this. Some might be a quantitative estimation in some cases. But basically, you're qualitatively assessing this to get a general understanding. Is it high risk? Is it low risk? Is the risk acceptable, or is it totally unacceptable and something needs to get done right away? So really, the likelihood and severity are two key components of risk. To get a more complete picture of likelihood, we use tools such as HAZOP and LOPA. And what I've displayed on the screen is a small fall tree that kind of integrates and shows how all these things come together. When you're looking at different scenarios and trying to understand how likely they are, or how which can help you understand importance when you blend it with the consequences, you're really looking at the accumulation of something that starts an event and the failure of those safety features that can prevent an event from occurring, from becoming something that's undesirable. On our left, we have a level control valve that may open up by either a valve malfunction, a controller malfunction, or an operator error. On the right, we have various protection layers that act as barriers between that initiating event and the ultimate consequences. And those protection layers can include things like safety valves, level alarms, and it's by failing all those that you can get to your ultimate consequences. When we're doing a HAZOP, the initiating event is often called a cause. In LOPA, it's an initiating event. When we're looking at whether a HAZOP or LOPA, we're looking at ultimate consequences. And when we talk about in a HAZOP scenario, we're looking at safeguards. When we're talking about LOPA, we're talking about an individual independent protection layer. So it's by pulling all those concepts together that we get an understanding of likelihood. And HAZOP and LOPA are good tools for doing that. Also, there's a little bit of background here on LOPA and some of the terminology involved. I'm going to hold off on that because there's something pretty exciting that's happening right now with respect to the development by the CCPS of an update to their layer protection analysis guidebook. That'll be coming out fairly, well, we'll be having a summary presentation on that fairly shortly as part of our webinar series. So we'll talk more about that at a later time. So now we've talked about how you can calculate likelihood of the event, the various tools involved. Pretty much that's all I want to, that's as far as I want to go with that. And let's start focusing on consequence analysis. The first thing to understand is what is the regulatory framework for that? Why do you do it in the first place? Well, of course, you want to understand risk, but there are also some key requirements for facilities that are covered by the risk management program regulations that are administered by the federal EPA or by the state accidental release prevention programs. Key elements when you're looking at all these programs as they put together, the first one is the hazard assessment, understanding how bad things can be, estimating potential release quantities, determining downwind effects, evaluating scenarios, potential exposure to populations, and also an accident history. Gives you a general appreciation of the magnitude of the hazard. This is typically blended with the prevention program, of which a key element is process hazard analysis. More about that in just a minute, along with an emergency response program in case things go awry and you have to deal with things that occur at the plant site. So those three key areas, the hazard assessment, the prevention program, and the emergency response program, work together to formulate the RMP. notice that one of the key elements is hazard assessment. More about that in a few minutes. When you're looking at the prevention program, it covers things like process safety information, process hazard analysis, operating procedures, training, mechanical integrity, management of change, pre-startup reviews, compliance auditing, incident investigation, emergency planning, and employee participation, hot work permits, and also contractor safety. When you're looking at all those different elements that formulate the prevention program, you notice that 5 of these are highlighted in red. Those are key elements that people get cited on very frequently and are a key part of preventing accidents from occurring in the first place. That process hazard analysis component is often implemented by a HAZOP study or other similar tools, along with perhaps layer protection analysis for very much more severe scenarios. It's that understanding of how what hazards can occur that coupled with the consequence analysis that give you an appreciation of risk, and then the other elements of the prevention program help you implement it to prevent the risks from occurring, or at least to minimize them. So now you see how the big picture fits together with respect to how you evaluate likelihood, how it fits into the prevention program, how it couples with consequence analysis, and how these are all wrapped together as part of the risk management programs that you may have to do for your facilities. Well, when you do the offsite consequence analysis from a regulatory perspective, they really key on 2 key items. One is a worst-case release scenario. Basically, the largest quantity of this acutely hazardous material, the substance that is being regulated, from a single vessel or process line that results in the greatest distance to an endpoint. We'll talk more about endpoints in a couple of minutes, but basically it's how far does it go before it can have a credible potential for severely injuring somebody. The other main category that is required from a regulatory perspective is an alternative release scenario. This is more likely to occur. They're more frequent events. Usually they're smaller in magnitude, but the EPA and your state ARPs want you to analyze a scenario that can reach an endpoint offsite, unless there's something that doesn't exist, which of course you'd want to justify. So when you're looking at things from a regulatory perspective, those are the 2 key categories you look at. They do that so that they can understand through the worst case analysis how important the facility might be in terms of protecting public health and safety. The alternative release scenarios are things that are more likely to occur that you really should account for with part of your emergency response plan. So that's how that dovetails and ties into your emergency planning process and the scenarios that you choose for that and the ones you train on. Also, as part of the regulatory requirements, you've got to determine off-site population impacts. That's the key thing that the EPA, as part of its charter in protecting the public, and also your state accident release prevention programs home in on as part of their charters. And they really want you to estimate the population within a circle of concern, or this radius of how far a release can go that can impact people, or how far the effects of a large fire or explosion at your plant site could impact. Populations include residential, institutions, parks and recreational areas, and also if you've got large concentrations of people in commercial, office, or industrial buildings. Using the most recent census data, all these items are free. If you're a practitioner or doing your own analysis, use the most recent census data. Also, population, when you do estimate it, should be to 2 significant digits. Off-site environmental impacts, given the EPA's charter and also the state program charters, are also to look at environmental receptors within that circle of concern. And again, there's a variety of tools such as USGS maps and other data that can help you identify those receptors. So those are the key reasons from a regulatory perspective of what you need to do and how you pull it together, and how that comes into play with respect to overall importance of risk. As a HAZOP facilitator and as somebody who goes through and helps clients identify the major potential scenarios that can have undesired consequences, you really need to have basic understanding of this off-site consequence analysis. And it's really important for helping you identify scenarios. Also, when you're doing a HAZOP study or other process hazard analysis, It can help you validate that the OCA scenarios are the ones to look at. It can also help you identify alternative release scenarios. And it's really important for the facilitator to understand the overall phenomenological issues, some basics of consequence analysis, how various impacts can affect population and plant workers, so that they can go back through and understand the dynamic response to the scenario so you can properly identify the appropriate safeguards to apply. So this is how it all fits together. If you're, whether you're actually doing the consequence analysis from a regulatory perspective to meet regulatory requirements, or you're understanding the consequences so you can help identify potential hazards, all these things kind of come together in terms of understanding the scenario, understanding the likelihood of the scenario, and the overall consequences so you can gauge importance and make definitive decisions on whether the existing safety features are adequate or whether additional features need to be deployed or built into your system. So let's talk about general modeling parameters and the kind of big picture items that you need to think about when you're doing consequence analysis. There's a lot of details that go into a lot of these different software packages, and by understanding some of the key driving forces or what really affects the results, you can simplify your work. You can also have a much better understanding and also a sanity check. If you're getting some results out of the computer, do they make sense or not? So one of the key things that drive this are what are called, another buzzword, endpoints. These endpoints are different for toxic materials and flammable materials. For toxics, if you think about what people get concerned about, if you're talking about releases that can go off-site from an industrial facility, you're really talking about things that volatilize or have a vapor pressure or are basically gases at ambient conditions. Ammonia and hydrogen sulfide are two of those examples of gases that can go and affect individuals off-site. And when you're looking at what can impact people, although everybody's different and everybody has a different response to exposure to chemicals, some people with health conditions or an acute sensitivity to certain materials can get affected at much lower concentrations, whereas some people who are very healthy may not be affected very much at all by certain concentrations that people consider hazardous. So toxicologists have established a median point, usually based on ARPG2 levels, of what concentration in air represents a hazard. For ammonia, the value is identified on the screen. Hydrogen sulfide, same thing. These are typically expressed in milligrams per liter, and these are available as part of the RMP guidance that's available on the EPA's website. So when you're looking at toxics, it's primarily the endpoint concentration that you want to be concerned about with respect to people impact. For flammables, there can be several impacts. Explosion hazards, or explosions or deflagrations that can generate an overpressure effect. 1 pound per square inch is typically a threshold, and I'll show you why in a few minutes, that they consider acutely hazardous. When you're talking about radiant heat or exposure, a heat of 5 kilowatts per square meter for 40 seconds is usually considered something that can be injurious to individuals and is something that people do not want to be exposed to. How you go about doing that is you also want to keep under the lower flammability limit. These flammability limits are chemical dependent. Each flammable material has a different lower flammability limit, and by keeping below that value, you're able to limit the potential for ignition and the effects of that, so that may be radiant heat or overpressure. So the endpoint is a key thing for understanding what the effects are for a potential scenario that can have an off-site impact. Another is wind speed and atmospheric stability class. Basically, which way the wind is blowing, and is the wind stable or not very stable. For worst case scenario, a lower speed and a higher stability class. More stable, lower speed means that you can build up concentrations at ground level where you would expect people to be normally. For alternative release scenarios, either if you don't have meteorological conditions and data associated with that plant site, a higher wind speed and lower stability that's more representative of an average wind condition is something that's allowed to be used for alternative release scenarios. So again, from a regulatory perspective, they want to take a look at the worst. They want to characterize the worst case scenario using the worst case wind speed and atmospheric stability class, whereas for alternative release scenarios, you're allowed to get a more reasonable or representative picture of what might realistically be expected to occur if you were to have a release. And of course, if you're just trying to understand risk, the appropriate conditions for the plant site, you might want to get a wind rose to get average wind directions, and also use an average stability are appropriate. Also things that...
Just real quick, this is Solveig Seda, the producer. I realized there were some problems with the invite, so I want to apologize to those of you who were not able to log on until now. There will be a recording available so that you can see the beginning of this presentation at a later date. Once again, I'm very sorry for the problem.
Did you want me to repeat? Do you want me to go over it again? I also have a rewind button over here too. All right, very good. Other key things that are associated that you want to keep in mind when understanding the potential for offsite impact is temperatures, highest daily maximums. Are we okay? Okay, good. Okay, highest daily maximum temperatures. There's some guidance documents that are provided in terms of high temperatures and also humidity ranges, and also for alternative release scenarios, or if you're trying to do a risk calculation to understand potential risks, using more average values or typical temperature and humidity data are more than appropriate. Another key thing to understand potential impacts are terrain features. What they do, again, if you're doing a worst case scenario, you want to use characteristics that are associated with rural that allow the materials to go farther, unless you can justify an urban configuration where you've got more variations in the height of the material close to the ground that tends to break up the flow pattern of the release and make the concentrations ebb faster. So for urban characteristics, you're likely to get smaller endpoint distances or smaller distances of where you might impact the public, whereas rural, when you got flat terrain, it can go farther. Now, both of these are assuming flat terrain. If you live in an area with lots of hills or a riverbed, you want to be very sensitive to the fact that if you've got a heavy gas release or something that's, we'll talk about more, we're talking about more buoyancy in a few minutes, but if you get a heavy gas release, that it might hug the ground and actually go to low points such as riverbeds or between hills and build up higher concentrations there. Now, if you wanted to get really fancy, there's a lot of very high-end models that can help you do that. But the most important thing, if you're at a plant site or if you're a contractor helping people do these calculations for a client, is to really understand what the potential impact of terrain features might be. And in so doing, really understand if something can be an acute hazard or not. So other things that need to be considered are mitigation factors. There's a lot of things that can help ameliorate the impact of the event. And when you're looking, again, if you're doing analyses for a regulatory perspective, you get two main categories: the worst case analysis, and also the alternative release scenarios. When you're doing worst case release scenarios, you can take credit for passive mitigation features. Things like dikes, enclosures, berms, drains, sumps, things that are there, they're passive, they're not going anywhere, they're more or less a solid feature that doesn't have to change its state to have its mitigation effect. You're allowed to take credit for that for both worst case release scenarios and alternative release scenarios. Now for active mitigation features, again, when your regulatory agency wants to characterize how bad could it be if there's a release from your facility, they don't want you taking credit for active mitigation features such as sprinklers, deluge, water curtains, neutralization systems, excess flow valves, flares, scrubbers, or emergency shutdown systems, or systems that may require power, may require somebody to activate it. They don't want you to take credit for that because a lot of times you can't count on those. So those are only something you want to credit for active release scenarios or when you're trying to get a really good understanding of the scenario when you're trying to accurately characterize risk at the facility. Again, keep in mind the reason why you're doing the consequence analysis in many cases affects the kind of modeling that you do, the assumptions that you make, and you've got three main bases. The worst case release scenarios that you do for regulatory agencies so they can understand the potential impact of your facility, the alternative release scenarios so you can model more likely events that you want to use for your emergency response planning, and also if you're just trying to understand risk. In the latter two cases, you want more realistic parameters, and you'll want to understand the progression of the scenario and take credit for active and passive mitigation features. So again, understanding the chemistry, understanding the phenomenology associated with releases and what happens to materials helps you understand, better characterize risk, and also understand things if you're a HAZOP facilitator, understand the whole scenario and what represents reasonable safeguards or not. So let's talk about flammables first. Basically, again, the key things that key offsite impact potentials are overpressure and thermal radiation. How hot can it get? Can it start subsequent fires? Overpressure events, what kind of impact that might have on people or buildings or equipment nearby. Now, also, if you're trying to address this from a regulatory perspective, a typical state ARP program threshold and also the federal threshold and also for process safety management is 10,000 pounds. If you're below that amount in your system or storage, you're typically not encompassed by these regulations. If you're over that amount, you typically are encompassed by the regs and have to do all these consequence analyses to directly meet regulatory requirements. Some things to keep in mind when you're trying to understand these various scenarios are different flammable materials have very different properties. I just took 4 common materials and put at the top hydrogen, methane, propane, and butane. From a molecular weight perspective and how they behave during a release, obviously hydrogen being one of the lightest, butane being a lot more heavy in terms of things that can volatilize, form gases, and go off-site. Very different boiling points. All in this case under standard temperature and pressure conditions are gases. When you're looking at dispersion characteristics, however, hydrogen and methane have a lower molecular weight than air and will typically be buoyant. Again, very temperature dependent. We'll talk about that in a few minutes. Propane and butane are typically behave as heavy gases. They're heavier than they have a higher molecular weight than air, and again, depending on temperature, would typically behave as a heavy gas. All these things are temperature dependent. Even something that has a lower molecular weight than air, such as ammonia, often behaves as a heavy gas because when it gets released, it tends to, as it transitions from a liquid to a gas, it tends to transfer heat to the environment, and it becomes then, it picks up heat from the environment, and also it's a much cooler material, so it behaves as a heavy gas. Propane and butane, if they're hot enough, they'll also behave as buoyant gases too. So again, you want to look at temperature and the chemical properties when you're deciding what can happen during a release. Vapor pressures can be much different. The enthalpy of combustion, again, there's a lot of information out there. The interesting thing is, on a per weight basis, the enthalpy of combustion, it's represented on this table in terms of kilojoules per mole, but the enthalpy of combustion tends to be relatively constant for a lot of the common hydrocarbons, of course, over a fairly small range, the kind of things you're going to want to look at, but a lot of the common hydrocarbons on a per weight basis. The lower explosive limits and upper explosive limits are also fairly similar for hydrocarbons when you're at least gaining an understanding of the general hazard potential. So understanding chemical properties, understanding behavior can help you understand a little bit better what represents reasonable risks and a realistic potential for having an acute offsite impact or not. Some of the things also, and these are just for your reference, I'm not going to go through this table. But I pulled this from one of the CCPS guidebooks on quantitative risk assessment, and this is a table of the kind of damage effects that you might get from a certain pressure potential resulting from an explosion or deflagration. At the bottom of this page, you'll see the 1 psi level, partial demolition of houses. Basically, they're made uninhabitable. This is one of the reasons why the 1 psi threshold is the one that's used for your endpoint, for determining endpoint distance for flammable materials. Is basically the degree of destruction is pretty significant, and it can have a big impact on nearby homes or businesses. So let's talk more about release phenomenology. You've got to keep in mind for flammables that fires and explosions need fuel, oxygen, and energy or an ignition source. You need to have all three elements to really have a problem. When you're doing regulatory-based consequence analysis, you've got to assume that a flammable material finds an ignition source, and you've got a certain amount of it that converts to energy, and then it gives you an endpoint distance based on that 1 psi threshold. When you're doing a more realistic model, there's other things that you need to consider. Keep in mind that there are a lot of conservatisms that you put into these worst-case scenario models. That finding oxygen, finding an ignition source, that may not be possible for certain types of releases. Not all the cloud will be in the flammable range. If it's not in the flammable range, it's not going to, it typically would not ignite and not participate in the energy that's associated with the deflagration or explosion. For a vapor cloud explosion, typically there's a 3% yield factor. That's much more realistic and much lower than the 10% of the cloud that participates in the explosion that would be assumed for a worst-case release scenario. So if you're doing a realistic assessment of this or trying to understand scenarios, these are things to keep in mind. Whether you're looking at toxic releases or flammable releases, they're typically superimposed on a map, and you're going to draw circles around what various overpressure impacts. In this particular case, you've got different endpoint distances for 1, 3, and 5 psi. So let's talk about toxic gases. A lot of the acute impacts are associated with toxic gases that may be used at a variety of industrial facilities that are scattered throughout your area, and also into a lot of urban areas that have a lot of housing too. When you're looking at airborne toxics, they're categorized like that. They're on the EPA's list if you have to worry about regulatory requirements for their potential for acute health effects. Typically, they're going to be a vapor at ambient temperatures or at standard temperature and pressure. However, in a lot of cases, small particle solids may also be encompassed by some of the state accidental release prevention programs. When you're looking at acute toxics, typically they're going to want to be a gas at room temperature, because if they're not a gas, typically they're going to stay on site unless they're a small particle solid. When you're looking at these sort of things too, you're going to look at things that are highly toxic and can cause toxic concentrations potentially beyond the fence line. I like this slide because it illustrates a lot of different things to keep in mind if you're looking at scenarios that can cause a yours may do that too. Flip back and forth. Okay. Basically, what we're looking at here is a vessel that's having a release that results in a vertical jet. Okay, it's a material that acts as a heavy gas, so it initially goes up until it transfers some of that vertical momentum to the air. As it's doing that, it tends to slow down, widen as it's dispersing, and then, of course, it's going to get carried by the wind. Now, there's also gravitational effects because it's a heavy gas. It gets carried by the wind direction on your slide is to the right, and then as it slumps, it tends to widen some more, and because it slumps, because it's heavier than air, it can actually travel upwind. And this is a phenomenon you have to be concerned about if you're an emergency responder, or if you're a person in a plant site trying to control a release. If you're dealing with a heavy gas, it can go upwind as it spreads out. Of course, depending on wind velocity, that would be for low wind conditions. Then as it goes downwind, it tends to spread more. And when you're thinking about these things, recognize they're spreading both horizontally and vertically as the gases are dispersing. That's why you see, as it goes to the right, these lines going up on your screen. And also recognize that as it spreads out more and more and more, eventually it gets to the point where it's really not above that end point where it can cause toxic effects. And therefore, basically, people refer to it as the cloud lifting. Basically, what's happening is your concentrations at ground level have decreased to the point where it's below the health impact that you're looking at. So, again, this slide illustrates some key effects that you want to be concerned about with respect to heavy gases, or gases that are heavier than air when released. When you're representing these typically, you're going to, okay. How are you doing over there? Okay, I need to restart. You may have to do the same thing. Okay. Good. It should go up here. Did you restart? Yes. Yeah, that's what I just did. All right. Mm-hmm. How you doing? All right, good. Are you here? Huh? All right, great. All right, so after we've looked at some of the key things that can go on with respect to your offsite impact, what I'd like to do is talk about some of the other things that can occur in general understanding of release phenomenology when you're having realistic releases. Basically, an understanding begins with understanding chemical properties. The phase at ambient conditions, whether it's a gas, liquid, or solid, is critical. As I mentioned before, things that tend to be gases at standard temperature and pressure are usually things that become more of an acute concern from a risk perspective, because if they weren't a gas, they typically wouldn't cross the boundaries of your plant site. Liquids can cause an environmental impact and can certainly cause pollution concerns, but often those are things that can be cleaned up. If you release a toxic gas at your facility, it's typically not going to be something that you can mitigate very easily. So what you have to do is understand the risk, do the consequence assessment, and make sure you have a prevention program that's robust enough to control things and keep things from going off-site. In this little example here, a lot of times you can have a vessel that's under pressure, maybe even liquids in the vessel, but the material, the chemical in the vessel wants to be a gas at atmospheric conditions and at standard at ambient temperatures. So if it's released and it goes in a dike, typically it's going to volatilize and get released. Also, when looking at a release phenomenology, the fire diamond is actually very helpful in terms of understanding general release characteristics. Typically, the NFPA diamond, you've got blue for health, red for fire, yellow for reactivity, and white for other kind of hazards. Gives you the general degree of toxicity, flammability, reactivity issues, and a general understanding of how dangerous the material is in terms of a potential for release, and then effects if it does get released. Understanding process conditions is also super helpful. If something's at high temperature, especially a liquid that's in a supercritical state under temperature and pressure, that if it's released, it will volatilize into a gas and go off-site. Those are critical things to understand of the various release characteristics. Also, the release mechanisms, the size of the leak location. If you get a vessel and you get a breach in the vapor space of the vessel versus the liquid space, it can behave very differently. In the vapor space, you may get a slower release to an equivalent of, in terms of the total mass released, to an equivalent sized leak. If it's below the liquid level, you may get material that comes out, and you'll get more mass release, but it might tend to puddle and then volatilize. One of the classic characteristics associated with this is when people talk about a chlorine freeze event. I've heard that term used quite frequently. Basically, people use that when you get a breach in the vapor space of a vessel containing liquid chlorine, and what happens is the vapor comes off, and you're taking the higher enthalpy material off the top of the liquid surface. More liquids volatilize, convert to gas into that vapor space, and then go through the vapor release. While it's doing that, it's actually cooling down significantly, and the liquid itself becomes cooler and cooler as part of an auto-refrigeration effect, and basically it'll stay as a liquid at very low temperatures and gradually absorb heat from the environment. So this chlorine freeze, from an emergency response perspective, was a term often used to describe the fact that you're getting a pool of liquid in the vessel, so that it really slows the release down significantly. So understanding where the release is, the various characteristics of the process associated with it, can really help you understand the phenomenology associated with the event and overall risk. The kind of things that you need to model when you're doing computer modeling are, for buoyant gases, you may have materials that come out and they come off an evaporating pool. We'll be talking about an example of that in a few minutes. Horizontal vertical jet releases. For heavier gases, things that are denser than air at ambient conditions or under release conditions, evaporating pools and horizontal vertical jets may also need to be modeled. Other phenomena that need to be modeled may be pressurized liquid releases, liquid spills of a pure substance, solution spills, vapor cloud fires or explosions, pool fires, oblivi, particulate releases, reactive chemicals, or chemical interactions with water vapor. All these different types of phenomenon, if you're doing an accurate software calculation, may need to be part of that software model, or at least it needs to be part of your understanding if you're trying to understand risk and some of the key things that may drive the magnitude of the consequences for a release. On this slide, I've identified a lot of the common software packages that are out there. RMP Comp is a freebie that comes from the EPA, a very simple model. And SLAB, Aloha, Screen 3, Negatus, FAST, Archie, and various CFD models are more advanced and can be used by the practitioner understanding the conditions. They're all good within certain release conditions and certain types of chemicals. And so you want to know what you're modeling, what chemicals are involved, and what range of characteristics that the software is good for. Okay, so now that I've identified a lot of the key things that you want to keep in mind with respect to consequence modeling and consequence assessment, a lot of the key software packages that are out there, and the key things you want to keep in mind when understanding the release phenomenology, I wanted to give you a couple of examples illustrating the range of consequence models required. First of all, I'd like to focus on a very common material that's used in a lot of different processes, and that's ammonia. You know, all of you are familiar. It's a colorless gas. It's quite odoriferous. It's very pungent. It's got a strong base. It can be highly hazardous. It reacts with people very readily, and can have very acute health effects. If it's inhaled, it can have very serious respiratory effects. Its high thermodynamic efficiency makes it a very attractive material to use in ammonia refrigeration. So very common uses for ammonia refrigeration, pesticides, and other chemical processes. One of the key things to keep in mind is in confined space conditions, it might also have potential for explosion if it's in high concentrations, often between around 16 or 25% in air. When you're looking at ammonia, it's considered relatively non-flammable. Again, you have to be in a confined space and within a very tight concentration range. Very serious health impacts, not highly reactive with a lot of materials or steels and other containment items that are out there. Other properties that you want to keep in mind is a very low boiling point. It also has an affinity for water, readily dissolves in water. It's got a relatively low molecular weight. When it disperses, because of its auto-refrigeration capabilities and a high latent heat of vaporization that make it a very effective refrigerant, it tends to as it's vaporizing, cool significantly and behave as a heavy gas when released. When you look at various saturation properties, this is just provided for background information. You'll notice that the boiling point, in this case in degrees centigrade, is depicted towards the bottom. Again, ammonia can build up a lot of pressure. We'll talk about that in a few minutes if it's in a confined location in piping. So when you're looking at ammonia, it can have a lot of different characteristics over a very wide range, behaving as a low molecular weight gas that behaves as a heavy gas initially and transitions as it warms up to ambient conditions to a buoyant gas. It can also build up very high pressures in processes and also has a very high affinity for water, and also has a high latent heat of vaporization, which makes it a very effective refrigerant, and it also affects significantly its release characteristics. When you're looking at release phenomenology, we talked about it. It can often be visible when it's released in air due to condensation of water. You're often getting a two-phase release. It can often come out in droplets. The droplets also increase the overall density of the release and convert slowly to vapor, keeping the plume cool and low to the ground, allowing it to behave as a heavy gas pretty far downwind. And it's a little difficult to see, but there's an aerial photograph of a very large release from several years back in the lower right-hand corner. One of the key things to keep in mind is because of its characteristics and because of the fact that it auto-refrigerates, if you get a liquid release, often the ammonia will cool into the diked area and appear fairly benign, slowly bubbling as it gets heat from the environment. It's very tempting to want to throw water on it if you're an emergency responder. A lot of times emergency responders want to use a fog mechanism to knock down vapors, is a term often used. Basically, to use the fogging mechanism to absorb some of the hazardous vapors from the air. Well, that may be a very effective mechanism for knocking down vapors. But if you take that a step farther and start applying it to a liquid pool of ammonia, what you do is you transfer heat into that ammonia pool. And of course, when you're transferring heat into it, even though you're diluting it a little bit, which is good, the fact is you're putting heat in rather rapidly, and you're going to have a rapid volatilization of the liquid ammonia in that diked area. So again, understanding the phenomenology, the chemistry, these materials themselves are very important for looking at risk, characterizing your consequences, and also understanding how you want to deal with emergencies. This is the slide I showed before. This would be typical for ammonia. Under low wind conditions, you could actually have a slumping effect. Just let it go. You can actually have a slumping effect that allows it to go upwind. Now let's talk about aqueous ammonia. Aqueous ammonia is basically ammonia in a water solution. A lot of people refer to it as aqua ammonia or ammonium hydroxide. It's often sold in a concentration below the requirements where the EPA considers it a highly hazardous material and wants to include it as part of a risk management program. When you're looking at general hazards, you're not really concerned so much about the aqueous ammonia unless it gets on the skin or you have some sort of contact with that. The primary hazard when you're looking at off-site effects is the ammonia vapor that comes off. And it's the same kind of toxicity issue that is associated with the anhydrous ammonia that I just discussed a few minutes ago. And of course, aqueous ammonia is also highly alkaline. As I mentioned before, ammonia's got a lot of different uses. Anhydrous is good for refrigeration systems. It's good for fertilizers. It's good for a lot of different chemical processes. It's also good for selective catalytic reduction and pH control. Aqueous ammonia has a lot of use for selective catalytic reduction in terms of NOx, reducing NOx emissions from power generation stations, and also for pH control. When you're looking at aqueous ammonia releases, again, understanding the conditions of the process and helps you really understand the what happens if it's released. If you get an anhydrous ammonia release, you may have to worry about cooling effects, auto refrigeration, heavy gas modeling, transitions to buoyant gases, two-phase releases, and a lot of different things that might go on. Aqueous ammonia is a lot simpler with the vapor release, but keep in mind that several different things are happening. If you get an aqueous ammonia release in liquid form, typically it'll come out in a liquid, it'll pool if it's in a contained area like a dike, and then you're looking at vapors coming off. So you're really looking, when you're trying to model this, you have to model how much liquid is coming out, the vapor pressure off the surface of the liquid, then once the ammonia itself goes airborne, how does that disperse downwind? Now the nice thing is it's typically going to be because it's lower molecular weight than air, around 17 for ammonia and around 29 for air, it's typically going to behave as a buoyant gas. So you'll need a couple of different models, understanding the vapor pressure, how much comes off out of the solution that was spilled, and also then looking at the dispersion of ammonia vapors. Good software packages for that. Slab does a good job. Aloha also does a good job. RMP Comp does okay, but it tends to overpredict the consequences associated with the release. The next page has a table that I'm not going to go into a lot of details, other than just to illustrate that when you're looking at an aqueous ammonia spill, vapor pressure really drives the consequences. Vapor pressure goes up significantly with solution temperature and also with concentration. So on your screen, if you look at the left, low temperatures, low concentrations have a very low vapor pressure, which means very little released. And as temperature goes up and as concentration goes up, as you move to the right and lower part of your screen, you'll see that you get a significant increase in the vapor pressure, which means is directly related to the amount of material that's coming off that solution. These are things that you definitely need to keep in mind when you're considering an aqueous ammonia spill. Also, other considerations, a lot of folks, to reduce the amount of material that is evolved from an aqueous ammonia spill, will often use a catch basin, basically an area that's fairly deep that can take a solution spill and minimize the surface area. Well, that does significantly decrease risk, even though the use of aqueous ammonia in the first place, if you're using it for NOx control or pH control, is a big improvement in lowering your risk and having a more inherently safer design. The catch basin can prevent vapors from ever getting to your endpoint concentrations or your toxic thresholds off-site. What that does is a lot of people use that to not only lower risk, but also it can be effective in limiting the potential for your being included in state accidental release prevention programs by making it not credible that it builds up toxic thresholds off-site. Also, when we're looking, we talked about anhydrous ammonia releases, what happens if you get a breach, and the heavy gas characteristics. We looked at aqueous ammonia releases and totally different phenomenology that need to get modeled. It's worth mentioning for a few minutes what happens for ammonia piping. A lot of people, and this has been a fairly common problem for refrigeration facilities and facilities that use anhydrous ammonia, is if you block in a section of piping and it starts at cold conditions and starts warming up to ambient, especially if it's impacted by sunlight, you can get a lot of heat put in there, and a lot of people have underestimated and really don't understand the magnitude of the potential pressure buildup in that blocked-in section of piping. What we did is something to help illustrate the magnitude of that. and the fact that you can build up several hundred psi in that blocked-in section of piping is to think about what ammonia is actually doing and to understand the chemical and what's happening. Ammonia, as in all fluids and most materials, tends to expand when heated. The fluid is somewhat compressible, but it's surrounded by piping, often steel piping that has certain limits in terms of how strong it is. And of course, the amount of pressure put on that piping is going to be dependent on, or the amount of stress put on the piping is going to be dependent on how thick the piping is too. So basically, if you're looking at ammonia blocked in and heating up, that ammonia that wants to expand and the pipe that wants to not expand as fast means that you're going to get a lot of wall stresses built up that reflect themselves in actual tensile stresses in the side of the piping. There's a handy-dandy equation for that if anyone ever wanted to look into it. It basically shows you that the pressure buildup, or that differential pressure, basically is the difference between the volumetric coefficient of thermal expansion of the fluid and the vessel itself. Basically, the fluid's trying to expand faster than the vessel. It's related to the change in temperature, compressibility factors, and it's inversely related to the thickness and also the elastic modulus of the vessel or piping materials. So these are things to keep in mind, and this is why you get significant increases in pressure as the temperature of a blocked-in section of piping increases. Again, understanding chemical characteristics and phenomenology are super important. What I'd like to do is very quickly show another side of the coin with respect to small particulates and what can happen. We've looked at ammonia, which looks at heavy gas release characteristics, aqueous ammonia, which is buoyant gas characteristics. Small particle solids can also, if dispersed at the plant site, have a potential off-site impact. Things that have small particle sizes can go up in the air, get carried with the wind, and being able to model that and look at the general hazards may be a requirement for people who use these kind of materials. Cadmium oxide, various cyanide materials, sodium cyanide, potassium cyanide, often are fairly small particles, and you've got to look at what the wind is doing, particle size, and the density of the particles, and how heavy you're going to get a reduction factor in the air. When you're looking at release phenomenon, basically you can get a drop effect that causes this puff of material that wants to travel downwind. That may also be something that needs to be modeled. That can also be handled by a lot of the common software models when you treat it as a combination of a gas, when you're looking at boundary conditions as a gas that's dispersing if the particle sizes are small enough, coupled with the airborne reduction factor based on the weight of the particle. So, what's the big picture? Basically, when you're looking at risk, you really want to understand both frequency, which you get out of a process hazard analysis or your HAZUP study, and also the ultimate consequences. Those ultimate consequences come out of a consequence assessment when you're looking at a gas release, and it's by understanding the two of them that you can get a better appreciation of risk. And both are critical things to keep in mind when you're controlling risk at your plant site or when you're dealing with the various regulatory requirements associated with RMP. I provided a couple of additional references at the end for your edification. And by the way, I'll open it up for questions in just a few minutes in case you want to raise some either by chat to our producer, Solveig Sather, or if you'd like to be unmuted and you'd like to initiate a discussion. These additional references, if you have other questions, you're also welcome to call us. And also what I want to let you know is coming up on July 12th is our next segment of our HAZUP study facilitation seminar series. And it's basically going to talk about some practical applications of a new, kind of a new challenge that's occurring in industry right now. More and more as engineering contractors are designing large facilities, they tend to use different subcontractors, different fabrication facilities from all over the world. And they tend to move a design fairly quickly. So we found in a lot of cases to help the project maintain progress, and also to be able to flush out potential weaknesses in the design early on, we've found a lot of benefit for doing design formulation and design review into the early stages of a HAZOP study, and kind of hybridizing a lot of the techniques to have not only more valuable HAZOP, but also flush out weaknesses and keep the project moving a lot more efficiently, especially when you're dealing with a lot of different individuals, subcontractors, fabrication facilities all over the world, and how important it is to kind of raise these issues early on. So that's coming up on July 12th. I hope they'll be very beneficial to everybody. And again, that's if you're part of our student population that's doing our HAZOP study facilitation seminar series, that'll be Module 9. So at this point, I'd like to open it up for questions. Or if you do have any after the seminar too, you're also welcome to give me a call. Everybody's pretty happy?
If you want to send a question via chat, go to the menu at the top of your screen and select Chat, and then select RMP Corp as the person you want to send the question to.
When you're doing your calculation for the accident distance, it's usually referred to as over the last 5 years.
Correct.
What if you have a facility that's been with us for 20, 30 years, and you look back 50 years, does that add any value?
All right, so the question is, for a lot of the RMP, risk management program requirements, there's a requirement for accident history summary over the past 5 years as part of your hazards assessment segment of that. The question was, well, what if you got an older facility that actually you have a great accident history even further back? I guess my response to this would be, that's terrific. That kind of track record substantiates a low risk if you can show it elsewhere. You're still going to have to do the consequence analysis. You'll have to do the other elements of the risk management program, but it certainly substantiates that you've got a low risk to the local population. And if you want to go beyond that and even list a longer term accident history, all the better. So, anything else? Anything else on this end? All right. Thanks to everybody for participating. Appreciate that, and we'll look forward to you guys on July 12th for our webinar on the design HAZOP studies. Thank you.